students. So for people who don't know Claudio, he's worked on a whole pile of problems related to how the lithosphere deforms, how the mantle deforms from geological, geophysical, geochemical perspectives. And today he's going to talk to us about how convection in the mantle can set where rivers, big rivers, flow across continents. I'll take questions. So if you can put the questions in the chat, please, as the talk goes on, and I'll put them to Claudio at the end. The talk's being recorded. Over to you, Claudio. Oh, just one more thing, please. If you're not speaking, go on mute and turn your video off. Thanks. Over to you, Claudio.
Thanks, Gareth. Thanks a lot for inviting me. I'm going to share my screen. So I hope you can see that.
Yeah.
Is that okay? All right. So thanks a lot, everybody. Thanks for inviting me. I'm very pleased and honored to be at Imperial College today. Even if it's online, I mean, it's a great pleasure, and I hope we will have a nice discussion all together. So today I'm going to talk about some of the progress we've been doing, trying to understanding what is the contribution of topography coming from deep mantle, and something that we call dynamic topography. And I spent most of my time working on the subject in converging margin, especially, for example, in the Mediterranean. And today we're going to move to a more to a subject that is more familiar to some of you, that is looking at large intracontinental river, like moving to North Africa and Middle East. And this is a work done in collaboration with a lot of friends and colleagues. I'm sharing the work we've been doing together. And so it's Thorsten Becker from UT Austin, Alex Forte from U Florida, and then some of the PhD that been working with me, like Andrea Sembroni, that has been working with me in Ethiopia mostly, and Peter Glisevic on the computational side, Eduardo Garzanti looking at the tritol deposit, and then Zoran Griezmann and Laurent Jolivet that gave me constraint on the geology. So please interrupt me when you want. If it's something not clear, feel free to step in, or maybe not. I don't know, Gareth, what is maybe afterwards or post question on the chat that actually I cannot see now. The topography is of course the major surface signal of the structure of the evolution of the Earth. So, but surprisingly enough, even though we know the topography fairly well at the high resolution, the region is still very disputed, and this is because the topography is the result of processes that are occurring at different level into the crust and to the mantle, and also on the surface. So their interaction produce a signal that is not always trivial to interpret. So here in this diagram, you're just showing that the crust is probably carrying out most of the signal in terms of static topography. But you may have also contribution from the mantle that is generally called dynamic topography, which is a transient feature related to the stress derived by convection at the base of the lithosphere. So it's a transient because it's full convection, so it may change in time. And also dynamic signal also on the surface, like related to the post-glacial rebound. So what we usually say is looking at topography, and there's an exercise that also the Imperial College, many of you have been doing, is to look at the residual topography, which is actually trying to look at the actual topography and see how they match the crustal thickness. And so when you do this exercise, you realize that you have a direct correlation that's showing that most of the topography is probably carried on by the crust, and so isostatically speaking. So in like an iceberg kind of models. But when you go, especially when you go in an interval of altitude that is between 0 and 2 kilometers, you have a large dispersal of crustal thickness that can match that between 30 and 50. And this showing that there's a lot of uncertainties whether the origin of that is related to some density change within the crust or something deeper, maybe into the mantle. And so when you do that, you try to filter out the isostatic contribution from the actual topography, and you end up with what we call residual topography. There is a map like that showing that apparently a lot of area are not under what we call isostatic equilibrium in terms of IRE residual topography. And some of these numbers are also pretty high. So what we can also do is to compare the residual topography that we obtain like that with the dynamic topography model. So taking mantle with the tomography and let the mantle convect. So converting basically the tomographic anomaly directly into temperature and look what happened on the surface. And this is the match that you may obtain. This is modeled by Bernard Steinberger. And you can also work on that and try to adjust that, considering, for example, eliminating the half space cooling, correcting that. But still, at the end, the correlation between the residual topography and the dynamic topography that you obtain are still very limited. And so we end up not being sure whether this signal is really a signal coming from the mantle or from something else. So the question I see on the ground, and the theory is simple for the dynamic topography, but the reality, capturing the signal of dynamic topography, is a difficult exercise, and also quantify that and having an idea on how long and how much. So one possible approach has been doing by the group of Garrett and Nikki, for example, for a long time, and is to look at for example, river profile, like using a linear inversion and coming out with some ideas, especially far away from a convergent boundary and from active boundary. So looking more in intracontinental setting, what the river can say. But also looking at the seafloor topography anomaly and looking what there is a discrepancy from the model, and so coming out with an idea that there may be a quite important signal even within continent and ocean of dynamic topography. We have usually take all the problem with a different approach, looking more at convergent margin and working more into the Mediterranean area, especially on orogenic belt, and looking what is the discrepancy between the crustal thickness and the evolution of orogenic belt, and looking at the mantle contribution. But today, I'm going to bring you in an area that has been investigated also by the group of Imperial College, so that's nice. We can have a discussion on that. And I will bring you to the North African Arabia system, where you can have an area that is very interesting for that, where you can have a large tomographic anomaly. This is a tomography between 140 and 400 kilometers from Yasmin, showing that there is a negative anomaly related to the subduction zone of the Tethyan slab, but also a large positive anomaly related to the presence of the Afar plume that is well centered below Ethiopia, low velocity anomaly. And this is the residual topography. So this is a spectacular area to understand the region of topography, looking at the big contrast with what you have on the northern margin with respect to what you have on the Ethiopian plateau and the Afar Horn of Africa. So this is the topography signal that you can see, and then we approach the problem looking more on the geological constraint that we can have, and especially working on the Ethiopian plateau and looking also at the Nile Delta. And so using Nile more like a tracer of the topography variation in time. So without looking really much on the real shape of the Nile River itself. And then the last part of the talk, I will show you some modeling where we try to reconstruct back in time the history of upwelling and downwelling of the area. So the Nile, it's a very interesting river, as all you probably know. It's one of the longest rivers on Earth. It has two tributaries, the White Nile, the joint of the Blue Nile, and the Pleistocene. Has been described for a long time as the cradle of civilization, as a limited discharge, about only 2,800 meter cube per second, but it wanders over the largest desertic and arid area of the Earth. So it's quite impressive, as you all know. It crossed 6 cataracts. It crossed the Nubian swell, so producing 6 cataracts here. And what is funny, though, is that its flow over such a long distance, only with 300, 400 meters of difference in elevation, or more than 3,000 kilometers of length. So this is quite impressive. So the story of the Nile is quite disputed. There is a model that proposed that the Nile, as we see today, or similar to the one we see today, is just a very recent story, started in the Holocene or in the Pliocene, just after the Messinian salinity crisis. Well, there is a bunch of other models that is proposing, based on different evidence, that the Nile, as we see today, was already running from the Ethiopian plateau down to the Mediterranean from the Oligocene. And this has been also a model proposed by the inversion of the river itself by the group of Hungarians. So with this idea in mind, we went to the Nile to look at the Nile source in the Ethiopian highlands. And the Blue Nile source is coming from the Lake Tana here in the region that have a nice cataract here. And the Ethiopian highland is really a spectacular landscape. It's one of the largest igneous provinces on Earth. And despite the beauty and the width of this area, actually there are very few direct constraints on the uplift history. And there are very few thermochronological data and very few data constraining also the morphology of the river and things. But the history and the elevation history of the Ethiopian island is pretty important. And actually has been used, the idea that this plateau was emerged and uplifted very recently, also push some people on thinking that with the based on also climate model, that the uplift in the Pliocene of the supposed uplift on the Pliocene of the plateau was triggering aridification and also the pushing Lucy to move northward in Europe. So it has a big impact. So we went there with this idea in mind. Despite this large literature on the study area, the geological and geodynamic complexity is of the Ethiopian plateau evolution matter of debate. So the shape of the topography and the area, if you look at the whole crossing the Ethiopian rift, it's a bell shape with the sides about 1,000 kilometers. And so you can see that the geometry of a dome-like, 1,000-kilometer long dome-like. The volcano is not there around 35, 40 million years ago, but the huge flood basalt erupted only from 30 to 28 million years. So it was a very rapid eruption with a placement of 10 to the 6 million kilometer cube of lava in a very short interval of time, and should have an incredible impact also on the climate system of the area. So we went there with the idea to unravel the topography evolution of Ethiopia, and we started doing a numbers of different methods. So we used thermochronology, paleoaltimetry, but nothing was working. And so I was a little worried also because Andrea Sembroni was doing his PhD there, and so has no result. And so we decided to use a more simple approach, just taking the flood basalt itself as a marker for unraveling the topographic history of the region. And so we went in the field and we started mapping out the base and the top of the basalt, the large igneous province, which is in orange here in this section. And you may appreciate that the base of the lava flow is actually uplifting and forming almost a bell shape here. And also we divided the lower the lower unit of the basalt with the upper one, so there are two large flow. And we start noticing that the largest flow was actually filling up paleo depression that is placed more or less in this area, meaning that there was a relief at the time that the basalt was emplacing. So that was pretty interesting, and we used those constraints to try to understand what was the topographic evolution of the area at the time. So this is the base of the flow, the trap, let's say the LIP basalt flow. So you're seeing that there is a depression here with two area that was at a larger elevation, on present day larger elevation, higher elevation. So we map the flood basalt thickness and also the top of the flood basalt. And with those kind of data, we start filtering out, restoring the topography back in time. We first of all take out the flexure related to the margin escarpment, which is something younger on the far, so producing a very, very impressive flexural system. And so we are storing that, and also the one that on the other side that is related to the escarpment, it's just erosional escarpment on the Ethiopian, on the western side. So the flexural, the reef margin is very impressive actually. So you ramp up and you have you can see the depression, the Afar depression from very high elevation and descending down to Afar with the numbers of beautiful normal fault and also the bringing calm that brings salt up in the highland. It's very impressive. And so after that, we take out the load, of course, related to the emplacement of the basalt itself. And also, we noticed that the base of the flood basalt itself was domed, was like forming a dome. They cannot be original. It should be something that happened. So after the emplacement of the basalt, there was arched and forming a large-scale arching. And we try to fit that with a filter. And so we eliminate also that kind of contribution. And so this is the relation to this flood basalt thickness, the contribution due to the loading of the basalt. And so we came out with the pre-flooding topography. And so pre-basalt topography, where you can already see that the region of the Tana region was probably one of the lowest area and the thicker part of the pile. And then you can go up when you close the Gulf of Aden and the Red Sea. Of course, the Yemen is here now. And then you have the Addis Ababa was already a quite large elevation at the time of the eruption. And then you can see also the contribution of the post-flood basalt doming. So all in all, along a cross-section that you can see before, our work was trying to construct a pre-flooding topography that bring us with an elevation of at least 1,000 meters in area nearby Addis Ababa, where it's now. And there was a quite undulate topography with large valley. So we don't know exactly the timing of this topography, but it was probably not too far, and probably in the Eocene, sometimes in the Eocene, just prior to the basalt emplacement, which occurred around 30 million years, as we said. And then there was this arching episode like that, so producing the doming. And then you have the formation of the Ethiopian rift, and then and with the flexure on the surface, and then you arrive to the present day setting. So this kind of constraint provide us the possibility to have a topography. Again, the Lake Tana here, and can say that the total uplift of the area was around 1,800 meters, and the remarkable topography. So there was already a remarkable topographic feature prior to the flood basalt emplacement, and then a large-scale doming occurring just after the flood basalt emplacement. And those are the three maps related to the topography. So what is also interesting is that when you look at the residual topography today, this is Addis Ababa again, it is impressive to see that we still have 600 meters of elevation that are not isostatically compensated. And so So it means at its center in Addis Ababa region, which is very similar to what you have also before. It means that we need to imagine probably something that is centered in this area that is still, at the moment, active, sustaining and supporting dynamically the elevation of the plateau. We look at the river to try to understand what was the story of the river itself. Andrea was carefully looking at the peak point variation and things. We found 3 episodes of base level change. And but we also think that the oldest one, which is one of the biggest one, is related to the capture of the internal drainage, integration of internal drainage that was active inside the plateau. That is actually bounded by these 2 escarpments with the flexural we were discussing before. That is producing a closed basin with internal drainage. And then probably there is another one that was younger. And the last one is probably on the Pleistocene, which is one of the most stronger ones, probably related to some maybe tectonics. And Andrea was very great on trying to also reconstructing the shape of this river internal drainage, and then the capture, the time of the capture and integration of the way it matched with the topography variation. We also considered the erosion of the plateau, of course, and we found out the new estimate of that is around 260, that is twice larger than what was proposed before. And this can be interesting when you go to the balance with what happened on the delta of the Nile now. The delta of the Nile, which is one of the largest delta river on Earth, but also the more populated one. You can see nice images here, and receiving 10 to the 6 tons of sediment, and 95% is believed to come from the Ethiopian highlands. So this is the isopac map of the Nile Delta. I'm not going to spend too much time on that. It's very well known, as you may imagine, for exploration on oil and gas, and there was big discovery also recently. There is the Messinian deposit. Below that, there is a huge deposition, and there is 2 lobes that are very well known, and this is the post-Messinian isopac map. The fully compacted sediment estimate is 580, so it's about twice the estimate that we have on the erosion of the plateau, anyway. At the time we were writing this paper, also there was the group of Eduardo Garzanti was also finding out, looking at the tridal zircon inside some of the borehole in the Nile, and they found actually traces at the very base of the Nile Delta, which is started depositing in the Oligocene, traces of zircon probably coming from the Ethiopian plateau. So this was the kind of shooting guns that saying that there was a connection already between the Ethiopian plateau and the Nile Delta at the time of the deposition. So we put in together the things. Those are the paleo elevation of the Ethiopian plateau in time, from before the flooding events, during flooding events, after, and then today. On the average elevation of all Ethiopia, and this is the position inside the Nile Delta. Those are the contribution of the Levant Basin, and this is the Levant plus the Herodotus Basin. And so you can see that those 2 guys go pretty well together. The onset of the position may match the onset of this paleotopography, and then go together. And so it's also saying that if it's true, the story that is, of course, very simplified, that those 2 things, the uplift of the Ethiopian plateau and sedimentation on the delta, was going together over a large interval of time, 30 million years. So now the question is why? Of course, why all this happened? What is supporting the topography variation in time, if like the one we reconstruct? And so we've been started doing this work a long time ago, and actually looking at the way convection was can maybe match by the tomography feature below the area. Our interest at the time was mainly to see why Arabia is moving this way, and what was the major contribution of this, if the subducting slab below the landing trench of the Afar plume was the major active driving forces for the Arabia motion. And we also try to match the anisotropy into the mantle, and we come out with a model where the Afar plume was kind of producing a convection cell joined with subduction in the Helenites, and this and also in the below the Beetles and Caucasus, and so this is forming a large convection cell that was producing, dragging also the Afar plume to the node and pushing Arabia toward the collision zone. So they're also very interesting. You can see that the residual topography we have today it's contributing very much on the topography signal, and also it's huge as also compared to the one we can model today using dynamic topography. So with this idea in mind, we start working together with Alex Forte. He had a very sophisticated modeling, new model, a joint model, where he tried with a viscosity profile, different viscosity profile, different tomography analysis. He was able to have a time reversing convection modeling that going back to 70 million years. And so this is assuming, of course, some assumption on the style of flow and on the layer viscosity. But the good thing is that you can really look at the result of the dynamic topography on the surface and see whether they match or not our reconstruction. And so trying to also tune and testing the sensitivity of the model over different viscosity profile, for example, of different tomography anomaly. And these are the results of the Alex work. So you have that the dynamic topography today is something like that, and back in time, 20 million years, is disappearing progressively. And when you run at 40, this is the Lake Tana, the dynamic topography signal was pretty low, just a couple of 100 meters. As you see, the scale is here. And then you can also appreciate the delta topography, so the variation in topography in time. And looking at that in the Nile Delta, you have subsidence during the last 20 million years. And this is, you have an uplift in the, where there's the cataract here between 20 and 40, and the uplift of the Ethiopian plateau in time. And so you can compare our data that we have on the specific region of the Ethiopian plateau with the modeling. And then you can see that the dynamic topography signal reconstruct on this model is make only 30% of the total topography gain. And this is quite interesting. It's probably meaning also that the rest, either the model is underestimating the dynamic topography amplitude, or that the rest of the topography gain, which is probably the most easiest solution, is related to some isostasy contribution, transtatic contribution. Going in the past is very interesting to look at what happened, for example, in the region. So in the 20 to 0 million years, you can see the difference in present to post flood basalt, 20 million years. So this is the delta Z. So you have like 800 meters of difference in elevation, and here we have only 400 meters, so almost half of that. And so the reason why you have this signal in dynamic topography is can be better appreciated looking at the section on the model that you can do in tomography. And then you see the downwelling in the northern region of the Tethys, and the upwelling that you have below in the area. And those systems, the south is here, the upwelling is here, the downwelling is there, is running over time with a pretty stable feature. So continuous upwelling, continuous downwelling. And the downwelling of the Aegean system into the lower mantle starts in the around 50 million years, and this is what has been also proposed by other people on the looking at the history of the Aegean trench evolution. Interestingly, so we can start looking at what was if there was a proto-Nile, PALEO-NILE before that, where it was running. And actually, interestingly enough, you can see that this is the model by our dynamic topography model, showing that at the site of the Nile Delta today, 50 million years, there was an uplift, and then the subsidence started only 30 million years, and then it's going to the blue. This is a section on that direction. The north is here. Therefore, this is giving an explanation of the fact that the subsidence and the accumulation of sediment start only in the Oligocene, and prior to that there was an uplift here, or there was a relief, and so it's probably if there was some river running, it's probably going more to the SIRTE rift in this area here. There was a rift where subsiding actually, and it starts subsiding in the Eocene. So and then probably the dynamic topography move somewhere here below the Nile Delta and attracting the river more to a northerly direction. Also, that is very interesting. Looking at the 6 cataracts, and we look at that, and it's funny, the motion of the river, the Nile, that go back and forth, trying to go around this Nubian swell here, and those are the trace of the 6 cataract. One of these is this one. It has been proposed that those features are a young feature, and maybe it's the case. For some reason, the model of dynamic topography that we ran was showing the pronounced uplift almost from 40 to 20 million years just in the area of the 6 cataract. This is a swell that has been produced by, of course, by some sort of intracontinental upwelling, and so it's probably a dynamic origin. Our model show that it could be that this is an older feature, and further investigation are necessary actually to really understand if it's the case or not. So what we learned from the story, first of all, I mean, this is a figure by Cox in 89, that was a very provocative measure paper, was suggesting that some of the feature in terms of river and topography may survive of a time scale of tens of million years. And they were referring to the Ethiopian dome. This is what we see, but also to other areas like in India or in South Africa, where you see he was proposing that some of the river was having the same shape, and some of the topographic dome attained at the time of the large Igneous province eruption, so tens of million years ago, are still there. So I don't know whether this is true or not, but actually looking at the dynamic support of Ethiopian island, we learned that the uplift history of the Ethiopian plateau is old. Actually, it's much older than what other people was proposing, looking only at the, for example, Nick point or of erosion that we interpret mainly related to capture and integration of internal drainage rather than really uplift. And the uplift is probably occur even prior to the placement of the lava dome. So we would be thinking around, I don't know, 40 million years. And this is actually in agreement with the numbers of other constraints coming, for example, with the pinch out and observation of the pinch out and the overlap of deposit, marine deposit on the Arabia, for example, peninsula while tilting. We found that the dynamic support has been so. We don't know whether it was a continuous story or a pulsation, but it's probably run for more than 40 million years, and with a wavelength of 1,000 kilometers and an amplitude of about 1,000 meters. So this is the numbers. So the origin of the long-term support, which is active today, because we still have 600 meters of non-isostatic topography below behind Addis Ababa, it's of course not clear. because many of the numerical model, for example, showing plumes and placement, what they found is that at the time of the plume and placement, just after that, the plume spread laterally below the lithosphere, and so just on top of a plume, you expect to have subsidence, actually, which is something that we did not observe. The place where we have originally at 40 million year, the main uplift is still there, and there's a center around Addis Ababa or so. So I think this is a nice images coming from the careful investigation of the structure of the mantle and the crust below Ethiopia, and showing that there is a very clear anomaly trapped into the mantle, the low velocity anomaly, that is clearly indicating presence of thermal perturbation and probably presence of also maybe fluid that are that are just located below the topography anomaly. So what is this? I mean, we need to think about a system that is continuously supported or intermittently supported by mantle flow, or maybe an anomaly that is trapped there that provide the dynamic support for the elevation in that area. And so maybe other region, like there are many other regions that may do the same, and some of them has been also there are nice contribution from your group, from Deccan, Madagascar, and South Africa. Maybe you have the same story. The other question that was more provocative is what we learn. We learned that the river may flow with the mantle. This is, of course, a cross-section and correspondence of from Ethiopia to the Nile, and they were showing the pattern of convection from one convection model run with Tostenbecker. The idea here is that the Nile was attracted more or less in this northerly direction because of you create a difference in elevation. This convection cell that is installed into the mantle from the Eocene onward, Oligocene onward for sure, was producing the difference in elevation and uplift and subsidence, just to attracting the river in that position. So this is an extremely exciting story because it means that the river may flow with the mantle, and we think that this is the case, at least for the Nile, that is descending down in a convection cell from the Egypt-Levant downwelling from at least 40 million years. It is roughly parallel to the SKS, not really parallel. Actually, we don't really have data on the Nile, but the SKS ran parallel to the rift zone, and so we can say more or less like that. So we thought anyway that this is the reason why you create a kilometer and a half of difference, peak to trough difference in elevation that force the river to the drainage pattern of the river. Of course, we don't know if the river was like that or was different, but just in terms of different elevation that forcing the drainage. And so on that concern, I think we may our data is very well along with also what the previous finding also of Garrett's and with the linear inversion found of rivers itself, that showing that much of the topography of Africa with the swell and the depression was actually occur long time ago, probably 30 or 35 million years ago. So this is very well in agreement also with all the numbers of other observations. And so I think this was exciting for me, moving from convergent margin going to intracatonic area to look at this kind of question. And also it is true that maybe we can really look at the river as tracer for mantle flow also for another region. I know the recent work in US, so maybe also I thought maybe it could have been nice to look at Siberia, although we don't really have a lot of SKS data, for example, there. And also I think, I mean, our model was very limited only to look at the dynamic topography evolution over time. so we didn't really match that with any landscape model. So probably the next step will be really to have a more coupled system where you can look at the surface expression of mantle dynamics with the landscape model, and also including all the crustal deformation. So this will be probably a very exciting possible next step on this kind of problem. So with that, thanks you for attention. And if you want to go to more on that, I mean, there is Andreas and Bruni done a lot of papers on some of the things that we were discussing. Thanks a lot.
Right. Thank you for training. We've got questions. If people have questions, could you put them into the chat, please? I don't think you'll be able to speak out loud. I've seen these terrifying things in Arabia, screaming at us across the canyons. They're moving packs. These baboons, terrifying. Anyway, thanks, Claudio. We've a question from Fred Richards. He says, it looks like the fastest rates of uplift occur quite a long time after the main trap eruptions, presumably due to the arrival of the plume head. Isn't this somewhat surprising? Is this trend maybe due to steady lithospheric thinning over time, i.e. hotter far anomaly gets closer to the surface as thick lithosphere is eroded away?
Well, of course, yes. We can consider that. I mean, we don't know where does the topography signal come from. So it may be static in this sense. I agree, it can be. So when looking back at this diagram that I was showing, we try to sorry. Okay. If you look at this, I mean, we try to divide in the different colors the contribution that what we think is going to be really static, like the load of the plateau, the load of the lava flow. Of course, it's a static feature. The erosion is a static feature. So this is really isostasy. And there are some of them that we don't know. This phase of uplift that you have after the emplacement of the lava flow, we thought as a very large wavelength. So you may have a contribution of about 1,000 meters. I agree, it's a lot. So just after the emplacement of the lava flow. We don't really know when it happened, so we don't really have any idea on the rate. It could be probably prior to the rifting event, so prior to 15 million years ago, and after the flooding stage, so 30. So our idea is that between 30 and 15. So now, what is the reason for that? The shape of the anomaly and the wavelength of the anomaly talk about something into the mantle, so it cannot be a crustal feature, and this is okay. But of course, we cannot exclude that you have, for example, some underplating, some crustal underplating occurring during the placement of the flood basalt. You can have, of course, crustal thickening. But what is, on this sense, what is really interesting is to look at the crustal thickness today, that we know very well from the study, from the Eagle project, from all the projects running in Ethiopia, that it cannot explain the whole topography elevation because it's too thin for that. So in that sense, I think you may have some contribution from the plating, but not too much. Concerning mantle lithosphere erosion, it may be possible, but you need to consider always that by thermal convection, you can erode the mantle lithosphere, but the contribution of the mantle lithosphere is minor to the crustal one, far minor. So to have 1,000 kilometer elevation only due to the mantle lithospheric reduction, you need to have 100 kilometers of mantle lithosphere that have gone away. And this is not what we see, for example, from the structure of the mantle today. So you may have a portion of that related to this problem, but cannot be too much. So the rest of that is probably related to some, should be probably related to some dynamic. But to be true, I cannot tell you how much is the one, how much is the other contribution.
Oh, you got a thumbs up. You preempted Ian's question to a large part of things. So Ian asked, Given that the Ethiopian traps are 2 kilometers thick in places, but also important too, perhaps, is the 7.38 kilometer per second lower crustal intrusion layer that likely formed at the same time. It's 8 to 12 kilometers thick. I think you've already done this, but he asks, can you comment on the contribution this might have on the topography, total uplift, and maybe uplift rates too? I think you've largely addressed that in the previous set of comments.
Okay.
If you want to say anything else, please do. If not, I'll move on to Victoria's question.
Okay.
Okay.
I mean, it's fine. I mean, if this, I mean, this is, if it's fine for you, I'm fine. I'm fine. I mean, well, you know, my problem is that the crucial problem is that we had this topography anomaly forming prior, after flooding, and what we have now as a residual topography is similar. It's still 600 meters of contribution, which is a third of the mean gain on elevation. So in time. So I think what we need to understand is how those systems of plumes work on. If it's possible to imagine that you have a system of a plume that may keep going, flowing for 30 million years or so, with a upwelling, maybe discontinuous upwelling, maybe pools of upwelling for 30 million years more. So this is something that I think we don't really have an answer from a modeling point of view. Maybe Saskia has ideas on that. I don't know, actually.
Okay. We'll move on to Victoria's question. So Victoria asks, 1, you mentioned the dynamic topography model doesn't account for the full uplift you calculate. Most dynamic topography models ignore the top 200 to 300 kilometers of the mantle. Did you investigate the possible isostatic contribution of the upper mantle? And then the second question, yes, is a question similar to what I have. What are the age constraints on the flood basalts, argon? Maybe the first one first. So I think Alessandro's models, I think he does include the upper couple of 100 kilometers.
Okay, so the model, you're right. Many dynamic topography models don't consider the lithosphere. Alex's model consider a viscosity layering. So the lithosphere become, in this kind of model, a more viscous upper layer, about 100 times more or less. I can show you the viscosity diagram that he's been using. We test several of them anyway. The role of the lithosphere is largely neglected, I agree, and it would be good to have a more realistic lithosphere in our dynamic topography model. This is one of the conclusions I gave. So in this sense, I think there's a lot to do to try to have real elasticity, for example, even though at this scale it's probably neglectable, but other contribution coming from the crustal rigidity and things. But anyway, many people thought that when you deal with a very large wavelength anomaly, the contribution of the lithosphere may be somehow reduced in terms of elastic contribution. Like in post-glacial rebound, they don't really consider the lithosphere. But I think it would be really important, actually. So yes, we have a sort of a lithosphere, but I don't think. And the second question is argon. Yes, is argon done? There's a nature paper I can give you the reference. Is on the slides I show, where they constrain one of the best section that you can have on the flood basalt in a constraint that the major eruption occur in a couple of million years only. So yes, it's argon.
I can't really. Is it Kiefer, maybe? I can't really, it's a long time since I looked at this stuff.
Yes.
Okay. I had a question about the argon dating and whether people had to go, maybe you've had to go calculating the incision rates from that incised dated plateau. This is something we've been thinking about in a few places, Arabia mostly. Yeah. So have you got incision? Can you put together a suite of incision rates?
So, allora, what we done, yes, we calculate the nick point and the incision rate from the our work was mainly looking at nick point distribution. Actually, we found three nick point mainly. One is about 2,500, if I'm not wrong. Another one at 2,000. Another one at like 1,000 meters. So we check whether this nick point was related to some variation in lithology or not. And and then we ran some celerity model for nick point propagation. And then we came out with this number on timing of that. I mean, I'm not sure whether the constraints on that are really good or not, but that's many of the models that has been used to say that the uplift was Pleistocene uplift was using incision rate of a lava flow. And one of these is a quaternary lava flow here, for example. And this is a work by Gani, for example, Gani and Gani. We thought this is related to capture, to river integration. So the river was the escarpment is here is producing a big flexure. So when the Blue Nile arrived to integrate the plateau drainage, I mean, it has to have a very sharp incision, but it doesn't mean that you're really looking at uplift. It may be only river integration. So we were caring about trying to consider the region of that. I mean, we discussed only base level change. We thought that the oldest capture, the oldest nick point here is related to integration of this internal drainage. And the internal drainage is very well seen. Even if you fly over Ethiopia, you can see traces of these old, even by Google Earth. I mean, abandoned river drainage meandering inside this, then afterwards integrated with a strong incision. And yeah, so to actually say whether it's tectonic or river integration, this incision, well, actually, we thought the first one is probably the plateau capture, that is the oldest one, nick point. The other one is probably, we don't know, maybe connected with local tectonic event, so uplift event. Actually, we cannot say. But I would.
Okay, thank you. We have one question.
At the end of the story, we think that most of the push on the idea that the plateau was uplifting very rapidly recently is not really supported by, can be interpreted in a completely different way.
Okay, thank you. We've one more question, Claudio, from Saskia. Yeah, we've 5 minutes to go, so one more question. So Saskia asks, pertaining to Victoria's first question, is the lithosphere in the Forte model not also of a lighter composition, which they need to match gravity in the geoid?
Yes, I mean, Alex's model is a joint model, so including geoid, plate velocity, so kinematic, geoid, and tomography. So what they're doing is basically to find out the best viscosity distribution into the mantle to provide the best match for those constraints. So it's a joint model. And it has a lithosphere, not compositional, just viscosity difference, of course. And it's exciting to see that. I mean, it really had a very nice result, actually. Then running convection, if you want to see I mean, I've been working on present-day convection only. I mean, never going back in time. It's extremely delicate process, of course, because you have to include all the anomaly and evolution of the anomaly that are vectored with the flow, and also by conduction is changing. It looks like it works, and also it has a very nice result also in other areas. So I think this is a way to go. Of course, there's a long way to go to have more refined model, but it's quite exciting.
Okay, thank you very much. We have time for one very quick question if anyone wants to put it in the chat now. Otherwise, we'll let Claudio go before he sees loads of us this afternoon. Okay, yeah, no more questions. Thank you very much again. That was great, very nice, clear talk. That's great. And you'll see you're getting virtual claps and a real one from me. You'll see Connor and Fred at 1 o'clock. But, you know, if you need to take a little bit of time to go and get a bit of lunch, don't worry, that's fine. No problem.
Okay. Okay. Thanks a lot, everybody. Big pleasure.
Thank you very much. Thanks. Thanks.
Claudio.